St. Joseph College for Women, Visakhapatnam. Welcome to St. Joseph's open web-based learning platform, So E-Learn, for its soulful and enriching e-learning experience.
General Chemistry, Semester 2, Chapter 4, Metallic and Hydrogen Bonding, Module 2, presented by Dr. B. Madhavi, Assistant Professor in Chemistry, Department of Chemistry, St. Joseph's College for Women, Autonomous, Visakhapatnam. The contents of Module 3 are hydrogen bonding, strength of hydrogen bonding, properties of hydrogen bonding, types of hydrogen bonds, factors affecting inter and intramolecular hydrogen bonds, factors influencing molecular properties. Hydrogen bonds or weak bond. The introduction of hydrogen bond. Hydrogen bonds are specific type of intermolecular forces. Hydrogen bonds exist between molecules that have NH bond, OH bond or FH bond. In a molecule, when a hydrogen atom is linked to a highly electronegative atom, it attracts the shared pair of electrons more, and so this end of the molecule becomes slightly negative while the other end becomes slightly positive. The negative end of one molecule attracts the positive end of the other, and as a result, weak bond is formed between them. This bond is called as hydrogen bond. In hydrogen bonding, a hydrogen atom links the two electronegative atoms simultaneously, one by a covalent bond and other by a hydrogen bond. Compounds having hydrogen bonding show abnormally high melting point and boiling point due to the fact that some extra energy is needed to break these bonds. Hydrogen bonding describes a type of permanent dipole-dipole intermolecular forces. Nitrogen, oxygen, and fluorine are highly electronegative elements, whereas hydrogen is low electronegative. When a hydrogen atom covalently bonds with nitrogen, oxygen, or fluorine atom, the bond formed is highly polar. This highly polar gives rise to permanent dipole-dipole forces between partially negative nitrogen, oxygen, or fluorine atom from one molecule and partially positive hydrogen atom from a neighboring molecule. These forces are called as hydrogen bonds. Hydrogen bonds only occur between molecules that contains nitrogen hydrogen, oxygen hydrogen, and fluorine hydrogen bonds. A hydrogen atom is made up of just one electron and one proton. Hydrogen atom is covalently bonded to a very electronegative element like nitrogen, oxygen, fluorine. Its electrons are pulled away from it and towards the more electronegative element. This not only creates a polar bond and leaves the hydrogen with a partial positive charge, but it also leaves the nucleus or protons of the hydrogen atoms exposed to one end. Unlike with other atoms that are able to form a covalent bond, there aren't any further electrons around the nucleus of the hydrogen atom. This means as the bonded electrons gets pulled away from it, one side of the atom has no electrons around it, and this exposes the single proton in the nucleus. A lone pair of electrons from a nitrogen, oxygen or fluorine atom from a similar bond form a neighboring molecule will be attracted to the partially exposed protons, giving rise to a hydrogen bond. Hydrogen bonding in water. Water is a classic example of intermolecular hydrogen bonding in water molecule. Oxygen is highly electronegative while hydrogen is less electronegative. This difference creates a polar molecule where oxygen carries a partially negative charge and hydrogen carries a partially positive charge. Because of this polarity, the hydrogen atom of one water molecule is attracted to the oxygen atom of the neighboring water molecule. This weak electrostatic attraction is called hydrogen bonding. Each water molecule can form up to 4 hydrogen bonds, 2 through its hydrogen atoms and 2 through its lone pair present in oxygen. This leads to a strong network of hydrogen bonds between water molecules. These hydrogen bonds are responsible for many unique properties of water, like high boiling and melting point compared to similar molecules, has high surface tension, has high specific and heat capacities, and ice having a lower density than liquid water. Hydrogen bonding in ammonia. Ammonia is polar molecule because nitrogen is more electronegative than hydrogen. This creates partial negative charge on nitrogen and partial positive charge on hydrogen atoms. Due to this polarity, hydrogen atom of one ammonia molecule are attracted to lone pair of electrons present on the nitrogen atom of another atom. This results in hydrogen bonding between ammonia molecule. However, hydrogen bonding in ammonia is weaker than water because nitrogen is less electronegative than oxygen. Ammonia has only few or one lone pair compared to two in water. Each ammonia molecule can form few hydrogen bonds, so the overall intermolecular attraction is lower than in water molecule. Hydrogen bonding in phosphine. Phosphine denoted by pH 3. Phosphine does not show significant hydrogen bonding. Although phosphine has a lone pair of electrons, it is much less electronegative compared to nitrogen or oxygen. As a result, the pH bond is almost nonpolar. This is very weak attraction between molecules. Because hydrogen bonding requires highly electronegative atoms like nitrogen, oxygen or fluorine, phosphine molecule does not have hydrogen bonding. Therefore, phosphine mainly exhibit weak van der Waals forces instead of hydrogen bonding, leading to much lower boiling point compared to ammonia. The strength of hydrogen bond. As hydrogen bonds are weak bonds, the strength of hydrogen bond lies between van der Waals forces and strong covalent bond. The dissociation energy of hydrogen bond depends upon the attraction of shared pair of electrons. It also depends upon electronegativity of the atom. Higher the electronegativity, the higher the bond strength. Hydrogen bonding is strongest in HF than in water and weakest in ammonia. It also depends upon size of the atom. Smaller atoms form stronger hydrogen bonds because they allow close approach. As fluoride is smallest from the other, so it forms strongest hydrogen bond. It also depends upon number of hydrogens that bonds. More hydrogen bonds per molecule increases overall strength. Properties of hydrogen bonding. Solubility. Lower alcohols are soluble in water because of hydrogen bonding, which can take place between water and alcohol molecule. Volatile. As the compounds involving hydrogen bonding between different molecules have higher boiling point, they are less volatile. Viscosity and surface tension. The substance which contain hydrogen bonding exists as associated molecules, so their flow becomes comparatively difficult. They have higher viscosity and high surface tension, the lower density of ice than water. In the case of solid ice, hydrogen bonding gives rise to a cage-like structure of water molecule. As a matter of fact, each water molecule is linked tetrahedral to 4 water molecules. The molecules are not as closely packed as they are in liquid state. When ice melts, these cage-like structure collapse and the molecules come closer to each other. Thus, for the same mass of water, the volume decreases and density increases. Therefore, ice has lower density than water at 273 Kelvin. Hence, ice floats.
Boiling point. Substances with hydrogen bonding have higher boiling points compared to similar molecules without hydrogen bonding. This is because extra energy is required to break the intermolecular hydrogen bonds. For example, the boiling point of water is greater than H2S, which is further greater than HCl and ammonia. Water has an unusual high boiling point due to strong and intensive hydrogen bonding between its molecules. Physical state. Hydrogen bonding affects whether a substance exists as a solid, liquid, or a gas at room temperature. Substances with strong hydrogen bonding are usually liquids or solids. Substances without hydrogen bonding are often gases. For example, water is liquid while H2S is gas and ammonia is easily liquefiable due to hydrogen bonding. Thus, stronger hydrogen bonding leads to a more condensed physical state. Acidic strength. Hydrogen bonding can increase acidic strength in some cases by stabilizing the conjugate base. In molecules where hydrogen bonding stabilizes the ion that is formed after losing H plus ions, then acidity increases. Example, hydrogen bonding in certain oxyacids helps in the easy release of H plus ions. However, in some cases, intramolecular hydrogen bonding can reduce acidity by holding the hydrogen more tightly. Basic strength. Hydrogen bonding can affect basic strength by influencing the availability of lone pairs of electrons. If lone pairs are involved in hydrogen bonding, they become less available to accept protons that leads to basic strength decreases. Example, ammonia is a weaker base in water due to hydrogen bonding interaction with water molecule. Thus, hydrogen bonding plays a crucial role in determining boiling point, physical state, and acid-base behavior of substances. Types of hydrogen bonds. Hydrogen bond is divided into two types: intermolecular hydrogen bonding and intramolecular hydrogen bonding. Intermolecular hydrogen bonding is a specific type of attractive force that occurs between separate molecules. It happens when a hydrogen atom which is covalent bonded to a highly electronegative atom like nitrogen, oxygen or fluorine feels an attraction towards the lone pair of electrons on a neighboring molecule of an electronegative atom. And intramolecular hydrogen bonding is a specific type of hydrogen bond that occurs within a single molecule. It forms when a hydrogen bond is covalently bonded to a highly electronegative atom like fluorine, oxygen or nitrogen that interacts with another electronegative atom with a lone pair of electrons located on the same molecule. Factors affecting intra and intermolecular hydrogen bonding. The first one is solubility. Intermolecular hydrogen bonding plays an important role in increasing in solubility of substances in polar solvents like water. When a substance is capable of forming hydrogen bond with water molecule, strong interactions are established between solute and solvent. In such cases, the solute molecule form hydrogen bond with water, which helps them to mix easily. As a result, substances like alcohol, sugar, and ammonia are highly soluble in water because they can participate in intermolecular hydrogen bonding. Thus, greater the ability to form intermolecular hydrogen bonds with the solvent, higher is the solubility of the substance. In intramolecular hydrogen bonding, the solubility decreases. In this type, hydrogen bonds are formed within the same molecule, so there is no opportunity for interaction with surrounding water molecules. Because the water satisfies its hydrogen bonding, it cannot affect from hydrogen bonds with the solvent. This reduces its ability to dissolve in water. For example, compounds with intramolecular hydrogen bonding such as orthosubstituted phenols are less soluble in water compared to their intermolecular part. Next one is boiling point. In intermolecular hydrogen bonding leads to a significant increase in boiling point. In this type, hydrogen bonds are formed between different molecules, creating a strong network of attraction. To convert the substance from liquid to gas, these intermolecular forces must break, which requires a large amount of energy. As a result, substances with strong intermolecular hydrogen bonds have high boiling point. In intramolecular hydrogen bonding results in a lower boiling point compared to intermolecular hydrogen bond. Here hydrogen bonds are formed within the same molecules, so there is a little or no attraction between different molecules. Since molecules are not strongly held together, less energy is required to separate them during boiling. Therefore, such substances are vaporized more easily. The next factor is viscosity. In intramolecular hydrogen bonding, the viscosity increases. In this type, molecules are strongly attracted to each other through hydrogen bonds, forming an associated network. Because of this strong interaction, the movement of molecules becomes restricted and the liquid flows more slowly. As a result, substances with strong intermolecular hydrogen bonding show high viscosity. Thus, stronger intermolecular hydrogen bonding leads to higher viscosity. In intramolecular hydrogen bonding, the viscosity decreases. Hydrogen bonds are formed within the same molecule, so there is less attraction between different molecules. Since the molecules are not strongly connected, they can move freely and are liquids which flows very easily. Thus, intermolecular bonding results in lower viscosity. The next one is physical state. In intermolecular hydrogen bonding promotes a more condensed physical state. Strong attraction between molecules keep them closely packed. As a result, substances with strong intermolecular hydrogen bonding are usually found as liquids or solids at room temperature. For example, water is a liquid due to hydrogen bonding, while similar molecules without hydrogen bonding may exist in gaseous state. Thus, intermolecular hydrogen bonding favors liquids or solid state. In intramolecular hydrogen bonding favors less condensed physical state since hydrogen bonding occurs within the molecule. There is a weak attraction between different molecules. This allows molecules to remain farther apart and move freely. As a result, such substances are more likely to exist as gases or volatile liquids. Thus, intermolecular hydrogen bonding favors gaseous or less condensed states. The next factor is acid strength. Intermolecular hydrogen bonding generally increases acid strength. When hydrogen bonding occurs between different molecules, it helps in stabilizing the conjugate base formed after the release of H plus ion. because the conjugate base is stabilized by surrounding molecules through hydrogen bonding. The loss of H plus ions becomes easier. As a result, the substance behaves as a strong acid. Thus, intermolecular hydrogen bonding enhances the strength by stabilizing the conjugate base. In intramolecular hydrogen bonding, acid strength decreases. In this case, the hydrogen involved in bonding is held within the same molecule, making it less available for ionization. Since the release of H plus ions becomes difficult, the acidity decreases. Thus, intramolecular hydrogen bonding reduces acid strength by holding the protons within the molecule. Next one is basic strength. In intermolecular hydrogen bonding, generally basic strength decreases. When the lone pair of electrons on the atoms like nitrogen or oxygen is involved in hydrogen bonding with other molecules, it becomes less available to accept a proton. As a result, the ability of substance to act as a base is reduced. Thus, intermolecular hydrogen bonding lowers basic strength by reducing availability of lone pairs. In intramolecular hydrogen bonding, also the basic strength decreases. Here the lone pair is already engaged in bonding within the molecule itself. Because of this internal bonding, the lone pair cannot easily accept a proton from outside, leading to reduced basicity. Thus, intramolecular hydrogen bonding reduces basic strength. Factors influencing molecular properties. Molecular polarity. The polar molecules generally have higher boiling points due to dipole-dipole attraction. The next factor is molecular size or weight. Larger molecules have greater surface area and more electrons, leading to stronger London dispersion forces. And the third factor is hydrogen bonding, a strong type of intermolecular forces that occurs when hydrogen is bonded to nitrogen, oxygen, or fluorine. Molecular states. Due to intermolecular hydrogen bonding, two or more molecules of a substance may get associated, resulting in the formation of cluster of molecules, as we have seen in case of hydrogen fluoride, water, ice, etc. Two molecules of acetic acid can associate together through intermolecular hydrogen bonding and forms a dimer. Thank you.